Today we're going to talk about the mechanical properties of TiC. The general applications of TiC are
from the phase diagram, we can observe that we have three isothermal reactions. The first one is the eutectic reaction, which is the reversible reaction between liquid and gamma titanium carbon plus carbon, which is this point. So this point is occur at temperature 2776 degrees Celsius. Composition is 60% carbon. Here, at this point. Okay, look at the second eutectic reaction, which include that reaction between liquid and beta titanium plus gamma titanium carbide. At this point, which occur at temperature 1646.5 degrees Celsius. The composition include is 4% carbon. Around this point. Okay. The third reaction, peritectoid reaction, is between beta titanium and gamma titanium carbide with the alpha. So the temperature is occur at this point, 920 degrees Celsius, with 0.61% of carbon composition.
Now, let us discuss the intermetallic compound that present in the titanium carbide phase diagram. Intermetallic compounds are generally formed when one metal with its titanium has chemical properties which are strongly metallic and the other metal with its carbon has chemical properties which are only weakly metallic. As a result, it will producing a new phase with its own composition, crystal structure, and the properties. These intermetallic compounds are almost always very hard, brittle, and have higher melting point. The higher melting point indicates that the high strength of the chemical bond in the intermetallic compound. Stoichiometric intermetallic compounds have a fixed composition. They are represented in the phase diagram by a vertical line but not area due to their stoichiometry is exact. From the titanium carbide phase diagram, we observe that the intermetallic compound have 50% of carbon. There are two types of solid solution, which is substitutional solid solution and interstitial solid solution. For substitutional solid solution, solute atom can substitute in a crystal lattice. The crystal lattice of the parent element or solvent is unchanged but may distort. For interstitial solid solution, solute atom fit into the space between the solvent or parent atom. It can form when one atom is much larger than another. Atoms that can form interstitial solid solution due to their small size are hydrogen, carbon, nitrogen, and oxygen. Now, let us discuss the solid solution of titanium carbide alloy. Substitutional solid solution is impossible to form because the solute atom which is carbon atom is not large enough that it can replace solvent atom which is titanium atom in their lattice position. So, for titanium carbide alloy, the interstitial solid solution form when the carbon atom is small enough to fit at interstitial site between the titanium atom. The carbon atom crowd into the interstitial site, causing the bond of the solvent atom to compress and thus deform. There are two phases that observed in titanium carbide phase diagram. The first one is alpha titanium. It is interstitial solid solution of carbon in hexagonal close-pack structure of titanium. It is stable below 882 degrees Celsius. Alpha titanium is stronger and more ductile. The second one is beta titanium. It is interstitial solid solution of carbon in body center cubic structure of titanium. It is stable above 882 degrees Celsius. It is soft and more ductile due to the larger number of slip pane in body center cubic structure. Larger number of slip pane means higher packing density.
The first method of improving materials properties is rapid heat treatment. So the procedure of rapid heat treatment is rapid heating into beta field, then the temperature until above beta transfers, then following by the air cooling or quenching process. The rest of the quenching is about 30 until 80 degrees Celsius. Then the alpha phase to form is suppressed and beta phase is retained. The martensitic transformation of inhomogeneous beta phase is accompanied by the complex diffusional redistribution of alloying elements. So the last step is aging. The temperature is about 650 degrees until 700 degrees. This process is reheating the alpha beta region to form the beta prime. So the small beta grains and dispersed alpha beta mixture is formed. So the decomposition of metastable phase produced, then ductility improves. So the final product, we will get the coarse grain and fine grain microstructure. So the mechanical properties will increase, for example, elasticity and tensile strength, yield strength, and ductility. These mechanical properties all increase.
The second method of improving material properties is using the strength hardening. Strength hardening same meaning as cold work or work hardening. Cold work is one of the most important processes that improve the strength of the alloy. Before hardening, the grain size in the titanium carbide alloy is larger and the number of grain boundary is less. This causes the titanium carbide alloy is high in ductility but low in tensile strength and yield stress. It is easy to undergo deformation. After strength hardening or cold work process, the grain size is reduced and the number of grain boundary is increased. This causes the titanium carbide alloy hard to deform and the yield strength increase but the ductility is decreased. The larger hardness means the better. There are a few examples of cold working process that can improve the mechanical properties. The first one is cold forging process. This process is performed at room temperature. The most common method in cold forging application are usually standard or carbon alloy steel. One of the most common type of cold forging is a process called impression die forging, where the metal is placed into a die that is attached to an anvil. The metal is then hit by a descending hammer and forced into the die. Depending on the product, the hammer may actually be dropped on the metal numerous times in a very rapid sequence. The second example of cold working process is the cold rolling process. Cold rolling process is a process by which the strip metal or strip stock is introduced between roller and then compressed and squeezed. The amount of strain introduced to determine the hardness and other material properties of the finished product. The third example of the cold working process is the cold drawing process. This process involves forming the required TiC geometry on cylindrical rod referred to as pinion rod. A cylindrical bar of the required material is drawn or extruded through a series of several dies, the last of which has the final shape of the desired tool geometry. The cylindrical bar is progressively deformed into the shape of the die to produce the desired tube form. Since the material displacements take place by pressure, the outer surface of the gear is relatively smooth and work hardened. The fourth of the working process is cold extrusion process. Cold extrusion is defined as a compressive forming process where the starting material is billet slab and the process is carried out at room temperature. During the cold extrusion process, deformation heating of the deforming material takes place at several hundred degrees. Deformation heating is the process of conversion of deformation work to heat. In general, a punch is used for applying pressure to the enclosed billet in the stationary die. Thus, the pressure can apply partially and completely as per the requirement.
Today I would like to explain about the example of engineering or industrial applications of titanium carbide. Firstly, titanium carbide is widely used in biomedical industry. As examples, the use of titanium carbide in artificial joints. Artificial joints is a metal or plastic part that is surgically implanted to replace a natural joint, possibly elbow or wrist, but usually hip or knee. Titanium carbide are known as the best potential candidates for artificial joints due to their good corrosion resistance, low elastic modulus, high strength, superior biocompatibility, superior hardness, high melting point, and chemical stability. Titanium carbide was considered as the first ceramic coating for the functional surfaces in total hip and knee replacement. Next, in aerospace industry, titanium carbide is used in engine applications such as rotors, compressor blades, hydraulic system components, and nacelles. It is because due to their high tensile strength to density ratio, high corrosion resistance, and ability to withstand moderately high temperature without creeping. Titanium carbide also are used in aircraft, armor plotting, naval ships, spacecraft, and missiles. Furthermore, titanium carbide is used in automotive applications, particularly in automobile or motorcycle racing, where weight reduction is critical while maintaining high strength and rigidity. And in many sporting goods such as tennis rackets, golf clubs, lacrosse stick shaft, cricket, hockey, and bicycle frames and its components. Moreover, titanium carbide are used in manufacture of wear-resistant tools, cutting tools. Cutting demands a sharp, keen edge for blanking punches, shears knife, rotating sticks, rotating slitters, and bed knives. The very fine, rounded, slippery titanium carbide grains nestle in a tough metal matrix to resist dueling and chipping. Lastly, titanium carbide in industrial punches, tools, and dies. Pickup and galling are frequent problems when metal rub against each other at high speeds or under heavy pressure. Exposure to titanium carbide micrograins at the working surface leave them in a relief and in effect minimize metal-to-metal contact. Their smooth, rounded structure offers an extremely slippery and non-abrasive surface for contact.